This video is an introduction to parent graph transformations. So I'm going to review this in talking about absolute value graphs, and we talked about this earlier in the school year. So as you're looking at this, I've written a generic absolute value equation here, and it's got its different parts. It's all written in letters, and the first thing we're going to talk about is what happens inside the absolute value. This number right here, which I've noted with an H, tells it to move left or right. And what I've written here in the box is something that might help us, and that's X lies. Okay, so whatever is written by the X is lying to us. So if it's written with a negative sign, we're actually moving to the right. And if it's written with a positive sign, we're actually moving to the left. So think about it that your X lies to you. So this equation right here, y equals the absolute value of x plus 5, we want to think about it plus 5 while we're moving to the left. So if I look at that actual graph, here's my parent graph, the absolute value of x, plus 5, it moved to the left, 1, 2, 3, 4, 5, and then it looks exactly the same, except it moved to the left. So that's why we're memorizing all of these parent graphs, all 10 of them, so that we can apply these transformations. These parent graphs are our anchors, and then we can either translate left, right, up, or down, or we can reflect, stretch, or shrink from there. But right now we're just concentrating on moving left and right. Here is another example, but here's our parent graph, our quadratic. But again, it's got that plus 5, so I'm thinking, okay, my x lies, so I'm moving to the left 5. So I've got that graphed here. Here's my parent graph of x squared. So originally it starts here at 0, 0, but I know I'm going to the left 5, 1, 2, 3, 4, 5, and so here's x plus 5 squared. And I want you to notice how it's written like this, plus 5 and then the square on the outside. It's important that you notice that and how that's written, and we're going to talk about that a little bit more in a second. Here's another example of a different parent graph shifted to the left 5. Here's the original parent graph, the log of x. Okay, and you notice that it crosses right here at 1, 0, shifted to the left 5, 1, 2, 3, 4, 5, and it crosses at negative 4, 0. And one more, just so that we're not thinking we always shift to the left. Here's our parent graph of the square root of x, and then we have the square root of x minus 1. So I know my x lies, so I'm actually going to shift to the right one. So instead of crossing at 0, 0, I cross here at 1, 0, and then I follow kind of that same pattern. Okay, now I'm going to look at what does this number on the outside do. Okay, instead of right next to the x, what does it do on the outside? Well, that's moving me up or down. Okay, so now I want to say, okay, well, y tells the truth. My x lies, my y tells the truth. So here's one where I have x squared plus 5. So it looks similar, but it's different than this. Earlier I did this, which told me to go to the left 5 because it was inside by the x, because inside by the x tells me to move right or left. Now it's not next to the x, it's on the outside, so this is actually telling me to move up 5. So let's take a look at that graph. Okay, if you notice, here's my original parent graph again, crossing at 0, 0, x squared plus 5, 1, 2, 3, 4, 5. Did tell me to move up 5. Okay, and I just wanted to compare that again with the one where we had x squared plus 5 in parentheses. X plus 5 squared versus x squared plus 5. They are very different, and you can see them, how different they are, and it's important that you notice the difference. Okay, we are just comparing this with quadratics, but you can again do this transformation with any of your 10 parent graphs. Now we're looking at the number on the outside, the a value. Okay, this has to do with your vertical stretch or shrink. Okay, if that number is greater than 1, it's going to be a vertical stretch, is the vocabulary term that we call it, but it actually looks skinnier. Okay, if it's less than 1, Okay, it's a fraction, it's a vertical shrink, but it actually looks wider. So here are a couple examples, again with our quadratic, where the blue is our original parent function. Here we have 3x squared, so that's a vertical stretch, but you can see again how it looks skinnier. Okay, as you look here, our original parent function is again in the blue. The one that's been transformed is in the red. Our a is 1/3, so it's a vertical shrink, but you can see how it does look wider. Okay, here, one more thing, this is the last thing I'm going to point out to you about graphing, is that if your a value is negative, the graph does reflect across the x-axis. So here's your original parent function, here's negative x squared, see how it reflects across the x-axis. And again, this can be applied to any of your 10 parent functions. Okay, this is a summary. Okay, your a is stretch, shrink, or reflect, and we can call that a dilation, especially your stretch or your shrink. If it gets bigger or smaller, that's called a dilation. This number on the inside moves it left or right, and that's a translation. The number on the outside moves it up or down, and again, that's a translation. And these movements can be applied to all 10 parent graphs. So what you should be able to do is write these equations for all 10 parent graphs, or if I give you an equation of any one, tell me how it moved. Okay, so you should have taken notes while watching the video, drawn some sketches, and be able to show me this in class tomorrow. If you have any questions, please come to CAB Morning.